Hello and welcome to this lecture in electrical circuit. My name is Sumit Kumar Chaube and today I am going to start a brand new topic in electrical circuit called network theorem. Till this point we were discussing various circuit analysis techniques like mesh analysis and node analysis, and these techniques are really very powerful techniques. But we have to develop all the equations, all the mesh equation or node equation in order to get the quantity of interest, which becomes cumbersome as the circuit becomes large. For example, if you have a very complex circuit in which there is thousands of node and thousands of mesh, then you have to develop first thousands of equation for those mesh and node, and then you can solve those equations to get the quantity of interest. For example, a voltage across or current through a branch of the circuit. Now this really becomes cumbersome as the circuit becomes complex and complex. Then these techniques kind of fails. They don't really fail. You can still solve that circuit using these circuit analysis techniques, but it's going to require more time. It's become cumbersome and often it leads to error in the calculations because there is thousands of equations to solve. Okay, to overcome this limitations, engineers over the years has devised different kind of theorems to deal with certain situations. Not all these theorems are going to be applicable in every situation. They are application oriented, but in that application they works really like a charm. So you don't really have to solve thousands of equation. You can get there, you can get your quantity of interest in a very few steps. So in those situations network theorems are really helpful. Okay, most of these networks theorems are very simple and very easy to apply. So in this lecture and in the coming lectures we are going to discuss these network theorem. We are going to become familiar with the superposition theorem and its unique ability to separate the impact of each source on the quantity of interest. We will be able to apply Thevenin's theorem to reduce any two terminal series parallel network with any number of sources into a single voltage source and a series resistor. And the same thing, the same network will be reduced to a current source with a parallel resistor using a Norton theorem. So Thevenin's and Norton theorems are kind of dual of each other. One is going to provide us a voltage source, another is going to provide us a practical current source. We are also going to learn to apply maximum power transfer theorem to determine the maximum power to a load or choose a load that will receive maximum power. We are also going to become aware of the reduction power of Millman's theorem and the powerful implications of the substitution and reciprocity theorem. So in the next lecture and in the coming lectures we are going to discuss all these theorems and we are going to learn their application. Okay, but before we learn any of these theorems we have to understand a very important concept from the system theory called linearity. Most of these techniques, most of these theorems are applicable to something called a linear circuit or a linear system. So we must first understand what is linearity, what it means and why it is so important. So linearity is a property of mathematical relationship. Since mathematical relationships are called functions, one can say that linearity is a property of the function. It basically says that input and output can be, if you draw a line between input and output, then that line has to be a straight line passing through origin. So for example, in this particular circuit here in the left hand side you have a linear system because it is a straight line passing through origin. So here you have your output y on the y axis and x is our input and x is on the x axis here, and the line between x and y is a straight line passing through origin. Whereas in the second case you have output y and input x, and the again the relationship between x and y is linear, you can say it's not linear, it's proportional. It's a straight line, but it is not passing through origin, right? So in this case it's not going to be a linear system. But this is rather a very simplistic view of linearity, and this is kind of not applicable in higher order function or in higher order relationship. So first we have to see linearity in its entirety, and then we will understand why this is so important. Okay, so when you generalize this concept to a higher dimensional function, a higher dimensional relationship between input and output, linearity means the property of being compatible with addition, also called additivity, and scaling, called homogeneity. These two functions together are called principle of superposition. Okay, so a system or a circuit element is going to be linear if it is following principle of superposition, and principle of superposition basically means additivity and homogeneity. Both of these property has to be satisfied. Okay, so before we discuss, we have to basically understand the notation. So our notation is like this: x is our input and our output is y. So y is basically f of x. Okay, now this function f, this relationship f, is either going to be linear or non-linear, right? So we have to discuss about this relationship. So when this relationship is going to be additive, for example, if we have two input, let's say x1, another input is x2, then for x1 your output is going to be y1, and y1 will be equal to f of x1. For x2 our output is going to be y2, and y2 will be equal to f of x2. Linearity says, additivity says, okay, we are discussing additivity. So additivity says that if you add these two input together, and then if you try to evaluate your output, let's that output is y, then this output will be equal to f of x1 plus x2. According to additivity, this output must be equal to f of x1 plus f of x2, individual output. Okay, so output due to addition is equal to addition of individual output. This is what means by additivity. Okay, and we will discuss about this in the later when we discuss one example, it's going to be clear. Okay, next we are going to discuss homogeneity. What homogeneity means is that we have our x as input, then output is going to be f of x equal to y, and when we have kx as input, where k is basically a constant, it can be complex and it can be real, it doesn't really matter. When you have kx as input, your output should be ky, right? But actually our output is f of ky, right? And y is basically equal to f of x, so this must be equal to k of f of x. So these two has to be satisfied, that f of x1 plus x2 is actually equal to f of x1 plus f of x2, and f of ky, f of kx should be equal to k times f of x. This is what is derived from homogeneity. So these two theorems, these two properties has to be satisfied for a element or for a system, for that system to be linear. Okay, so now we are going to test going to apply this theorem to some of the circuit element that we know of. So the very first circuit element for which we are going to apply this is resistor, right? Now for resistor R, terminal relationship is V is equal to I times R, right? So I can be our input and V can be output, or V can be output and I can be input. Okay, so any one of them can be output and any one of them can be input. It doesn't really matter what point of view we are taking. For the sake of analysis, I'm going to take I as our input and V as our output. Okay, so you can simply see here that this is a very simple linear relationship, because it's this relationship is basically a straight line passing through origin, isn't it? So it's actually equation of a straight line passing through origin, isn't it? So it's very easy to see that this is a linear relationship. Without doing much of the analysis, one can easily see that this is the relationship of a straight line which is passing through origin. So it must be a linear relationship. So R is a linear circuit element. Another way of looking at it is by additivity and linearity property. Let's say we have our input I is basically K1 times I1 plus K2 times I2. Okay, and output due to I1 is V1, right, and output due to I2 is going to be V2. Then V2 will be equal to I1 R, sorry, I2 R, and V1 is going to be I1 R, isn't it? Right? So here you can see here that our output, overall output due to this I is going to be V, and V is going to be I times R. If we replace I by K1 I1 plus K2 I2, what we are going to get? K1 I1 R plus K2 I2 R, isn't it? And K1 I1, K1, so you can write it like this: K1 times I1 R is basically V1, so K1 V1 plus K2 V2, isn't it? So when our input is of this form, K1 I1 plus K2 I2, our output is also of the same form, K1 V1 plus K2 V2. So it is satisfying both additivity and homogeneity simultaneously. It means it is satisfying principle of superposition. It means that resistor is a linear circuit element. The next example that we are going to take is that of a capacitor. So we already know that for a capacitor, terminal relationship is I is equal to C dV by dt. Now for the sake of analysis, I am going to assume that V is our input and I is our output. So V, let me assume again V as K1 V1 plus K2 V2. Then I due to this, and again for V1 your output I1 will be equal to C dV1 by dt, right? For V2 our output I2 will be equal to C dV2 by dt, isn't it? So when we apply this, then our I is going to be C dV by dt, and if we put the value of V, K1 V1 plus K2 V2, where K1 and K2 are real or complex constant, then this will result into K1 C dV1 by dt plus K2 C dV2 by dt, right? And you can also write this K1 times I1 plus K2 times I2. So when input is K1 times V1 plus K2 times V2, your output is K1 times I1 plus K2 times I2. So you can actually see that this relationship C dV by dt I is equal to is also a linear relationship. It means capacitor is a linear circuit element. Similarly, one can show that inductor is also going to be a linear circuit element. So I mean, I'm not going to do that. You can try that at home. Now we are going to look at a voltage source. We have to determine where the voltage source is linear or not, right? So to do that, I'm going to plot current and voltage relationship for a voltage source. That's very simple. You see that voltage across the terminal of a voltage source is always going to remain constant, no matter what is the value of current. Okay, so here on the x-axis we have our current, and on the y-axis we have our voltage. Then you can see that voltage is also always going to remain constant no matter what is the value of current I, whether current I is 0, whether the current I is minus 10, whether current I is plus 5, it's always going to remain, voltage is always going to remain constant across the terminal of a voltage source. And this is what we mean by voltage source, isn't? So you can see that this is not a line of a straight line, this is actually a straight line, but this line is not passing through origin. So voltage source is a non-linear circuit element, non-linear circuit element. Okay, similarly current source can also be proved to be a non-linear circuit element. So with this discussion I am going to complete this lecture, and I will see you in the next one, where I will be discussing principle of superposition, or what is called as superposition theorem, which is a direct result of, which is, you can say, linearity is and superposition is vice versa. There is not much difference, but we are going to see that superposition theorem in the action. Okay, thank you.